Welcome to the third series of lectures on functional analysis. So in this lecture, we will introduce the Lebesgue-Bochner integral and discuss its properties. So students are assumed to be familiar with measure and integration theory. Those who are not familiar, you can read the section on measure theory in the lecture notes. So let's start with a measure space or a pre-measure space. So we have a triple x, a, and mu, which is a pre-measure space. By this, we mean that X is a set, a non-empty set. Okay. And then A is a collection of subsets of X. So that's a subset with the power set of X. Is an algebra on the set X. Okay. So these are the subsets where we can assign what we call a numerical measure or numerical pre-measure. And there are three properties for an algebra. The set X must be in the algebra. It must be closed under complementation. So if A is in the algebra, then so is the complement relative to the set A. And finally, it should be closed under finite unions. So if you take two elements of A, say A and B, then the union must be also in the algebra. Okay, from this, we could extract further properties. Okay, so from the first and then the second, so taking the complement of the set X would be the empty set. So the empty set should be also in the algebra. And applying 3 and the principle of mathematical induction, suppose you have n sets in A, then the union of these sets, and then by applying the Morgan's law and the second property, one could also show that the intersection is an element of the algebra. So therefore, an algebra is closed under finite unions and finite intersections. And finally, applying the fifth property and the closure with respect to complementation, if I have two elements in the algebra, then the difference, which is basically the intersection of A and the complement of D, must be also in the algebra. So that is what we mean by an algebra. Finally, the function mu is defined on the algebra to the set of extended real non-negative numbers. So here we allow an infinite value of the pre-measure. For instance, you can think of the counting measure. So if your set is infinite, then the pre-measure or the counting measure is also infinite. So this is a pre-measure on the algebra X or on the set X. So by a pre-measure, we mean the following. So the pre-measure of the empty set must be 0. Okay. And then it must be sigma additive. And by this, we mean that if you have a countable collection of elements in the algebra, which is pairwise disjoint, then, and at the same time, the union is also in the algebra, Take note that we need to postulate this since we are not guaranteed that the countable union of elements in the algebra is an algebra. Well, this property is satisfied if you have a sigma algebra. But in this case, we only have an algebra. So if you have a pairwise disjoint collection, countable collection of elements in the algebra having a union in the algebra, then the pre-measure of the union should be equal to the sum of the pre-measures. And this is sigma additivity. So then, a pre-measure space is a triple where the first component is a set. This is the collection of points where we are interested in. An algebra on X. So this is the portions or subsets of the ambient space X, wherein we can assign a pre-measure. And the third component, mu, is a pre-measure wherein the pre-measure of the empty set must be 0 and it is sigma additive. Okay, so that is what we mean by a pre-measure. Next, we will suppose that Y is a Banach space over the field K. We call that K is either the set of real numbers or the field of complex numbers. With this, let us define what do we mean by a simple function. So a function from X to Y will be called simple if the range is finite. So f of x is finite and the inverse images of singletons, well, more precisely, we should write this with a parenthesis, but for simplicity of notation, we ignore the parenthesis, is in the algebra for any y in the image. And the pre-measure of this inverse image of the singleton y is finite for every y in the range except possibly 0. Okay. So that is what we mean by a simple function. So the range is finite. The inverse images of each singleton consisting of elements of the images will be in the algebra, and then the pre-measure of these inverse images should be finite for any point in the range except possibly at 0. Okay, so we will denote by S of x a mu, so that's the pre-measure space. And then the fourth argument is the codomain, the y, to be the collection of all simple functions from x to y. And if the Banach space y is the field of K, then we suppress the fourth argument. So in other words, S of x a mu is the set of all simple functions with respect to this pre-measure space having values in the field K. Okay. Remark. One can show that the set of simple functions is a subspace of bounded functions from x to y. Well, that follows immediately because f has a finite range. Simple functions have finite ranges. And moreover, the norm of a simple function, f, belonging to this space is a simple function having values in the field of real numbers. Okay. So with this definition, a simple function in this pre-measure space with values in y can be represented as follows. So here f is the sum of the images of y, and then times the indicator function of the inverse image of the singleton y. So take note that this is indeed a finite sum because f has a finite range. And then recall that the indicator function of a set A. So let us recall the definition here. So the indicator function of A, a subset of X, is defined to be, so this is a function from X to, let's see, the set of reals, okay? So it is either 0 or 1, depending whether, so if it is 1 if X is in A, if X is not in A, then it is 0. So this is just what asking whether an element X is in A or not in A. So that's the indicator function. Okay. Now, we define the Lebesgue-Bochner integral of this simple function f as follows. So having the above representation, so the Lebesgue-Bochner integral will be denoted by this. So the integral of f over x with respect to the measure mu. So this is the sum over all images of x or of f. So take the image, then take the pre-measure of the inverse image. Okay. So ideally, if we look at, for instance, take the following simple functions and illustration. Suppose this is x, and you have, let's say, a height that is either 1 or 2. And everything else is 0. So let us take that one as 0, and then as well as the outside part. So on the left, it is also 0, and on the right, it is also 0. Okay. So again, the graph would consist of this portion, and everything else is 0. So let's say this is the graph of your simple function f. Okay. So the height would be 1 and 2, and this interval here would be the inverse image of 1, and then this would be the inverse image of 2. Okay. So the area of this or the area under the curve of this simple function, well, borrowing the idea of the Riemann integration, that is the integral of the function over x. Okay. So in this illustration, x would be the set of real numbers, and y would be the set of real numbers. So for the first one, the area would be the height, which is 1, times the length of the inverse image. The second one would be the height, which is 2, times the length of the inverse image of 2. Okay, and then you take the sum. This would be the integral of f over the function x, over the domain x. Take note that here, if f is 0, then there's no contribution on the area, hence of the integral. Okay, so with this, you can think of this as your height. And then you can think of this as your base. Now, with the convention that 0 times infinity is 0. Okay. So here, this would be your height. So no matter how, no matter what is the pre-measure of the image of the 0, ideally, this should not contribute on the area, hence on the integral. So following this convention, we could exclude 0 in the image set, and we should get the same Lebesgue-Bochner integral. Okay, so that's the definition of the Lebesgue-Bochner integral of a simple function. So you take the height, that's the y. You take the length of the base, that's the pre-measure of the inverse image, and the product would correspond to the area of this region here. And if you take the sum, that would be the Lebesgue integral, or Lebesgue-Bochner integral. Okay, so the construction is similar to the Lebesgue integral, the usual Lebesgue integral. And with that, we have indeed analogous properties, which we state without a proof. So the proof here can be established following the proofs in the usual Lebesgue integral. So let us summarize these properties. The first one is independence with respect to the representation of the simple function. Okay, by this, we mean that if I have another representation of the simple function as a finite sum, let's say k from 1 to m, y sub k times the indicator function of a sub k. Here, y sub k is in y. A sub k is in the algebra. Okay, so take note that here, y sub k's are not necessarily distinct, and the a sub k's are not necessarily pairwise disjoint. And the image of, or the pre-measure of the a sub k's are finite for all k. Of course, except when your yk is 0. Okay. Because here, if yk is 0, this will not contribute in the integral. Then I can use this representation to calculate the Lebesgue integral of this simple function. So you take the sum over all k of the images times the pre-measure of the sets A sub k. Okay. So one can show that indeed this sum is a simple function, and if we have this simple function, then we can use this representation to calculate or to compute the Lebesgue-Bochner integral. One can also show that it is linear. So the Lebesgue-Bochner is linear, which means that for any scalar alpha and for any simple functions f and g in this pre-measure space with values in y, the Lebesgue-Bochner integral of the linear combination is the linear combination of the Lebesgue-Bochner integrals. So that's linearity of the integral. So here we have integration over the whole set x. Now, if I have a subset of x that is in the linear or in the algebra, okay, A in the algebra, we will define the integral over this set A of the simple function f as the integral over x of the product f times the indicator function. Okay. One can show that this is also a simple function, hence this integral on the right is well defined. Okay, so with this, we have, let's say, the monotonicity property. Okay, or before that, we have here the additivity, which means that if I have two elements of the algebra, say A and B, pairwise disjoint, so the intersection is empty, and I have a simple function f, this pre-measure space with values in y, then the integral of the over the union of f should be the sum of the integrals over A and over B. So integrating over a pairwise disjoint union is the same as integrating on each sets and then taking the sum. Next, we have monotonicity. So suppose I have two simple functions f with values in R. Okay. So let us emphasize that one. Here we need this so that we can talk about order relations respectively. And f is less than or equal to g, mu almost everywhere. Okay, and what do we mean by this? We mean that okay, so take note that a property holds mu almost everywhere if the negation of that property holds in a set of measure at 0. Okay, so what do we mean by this? If we take the outer measure of this set, okay, So the set f greater than g is an abbreviation of the following set. So this is the set of all x in the domain wherein the inequality holds. Okay. The outer measure should be 0. So again, since these are, by the way, simple, so it is enough to consider the pre-measure. Okay. So f less than or equal to g mu almost everywhere means that the set where the inequality is violated has a pre-measure as 0. Okay, a while ago, I mentioned that this is the outer measure. One could also formulate this in terms of the outer measure, m star. So what would be the outer measure generated by a pre-measure? So let us recall the definition. The outer measure induced by the pre-measure mu would be a function which we denote by mu star. So now here, the outer measure is defined on all subsets of x. So the outer measure is defined as follows. So for any subset b of x, or b in the power set of x, the outer measure b is defined to be the infimum of the sum of pre-measures covering b. So b is a subset of the countable union of the a sub n's, and the a sub n's are in the algebra. Okay, so let us write that down. A sub n is in A for all n. So that is the pre-measure induced, or I should say the outer measure induced by a pre-measure. And it is well known in measure theory that the restriction of the outer measure over the algebra coincides with the original pre-measure. In other words, the outer measure of A is the same as the pre-measure of A, provided that A is in the algebra. Okay, so going back here, take note that this set, one can show that this is in the algebra. Okay, hence the pre-measure under mu and the outer measure would be the same. So you can put the asterisk, or you cannot, or you could remove it. Okay. So that is what we mean by f less than or equal to g almost everywhere. If this is valid, then the integral of the smaller function is less than or equal to the integral of the larger function, g. Okay, so here we neglected a set having measure 0 because you could see that indeed sets having measure 0 will not contribute on the integral. Okay. And from this monotonicity, it follows immediately that if I have a simple function with values in R, and we have two scalars, say alpha and beta. So alpha is the lower bound of f, and beta is an upper bound, okay, of f, mu almost everywhere. So alpha and beta are real numbers. Then if I integrate f over the set A, this is less than or equal to the upper bound times the pre-measure of A, but greater or equal to the lower bound alpha times the pre-measure of the set A. Again, here A is an element of the algebra. So there's of course, a geometric interpretation of this. Suppose you have, in the real case, you have this function f, and you want to integrate over A, and A is this interval here. Okay. Now, if you look at the lower bound, in this case, the lower bound is the portion here, located at the left endpoint, and the upper bound will be located on the right endpoint, at least in this example. The upper bound would be this part here. So this is beta, the height of this rectangle. So take note that the area this portion here would correspond to alpha times the pre-measure of A. Okay, so to have a clear graph, let us copy this. And let us put down here. On the other hand, this would be the upper bound. Okay, so again, this region here is alpha times mu of A. The area of this region here would be beta times mu of A. So the area under the curve would be between these two regions. So that's the geometric interpretation of this one. And finally, or the next property, I should say, if I have, let's say, a simple function in this pre-measure space with values in R, two elements in the algebra, one is a subset of the other, say A is a subset of B, and F is greater than or equal to 0 almost everywhere. So we have a non-negative simple function almost everywhere. So this means that the set of points where F is negative has measure 0, or outer measure 0. Then the integral over the smaller set is less than or equal to the integral over the larger set. I would like to emphasize that this condition here is crucial. So, well, to give a simple example in terms of the Riemann integration, let us consider, let's say, the function f. from R to R. So this is, let's say, the sine function. So take note that this is not non-negative. So there are values wherein this is negative. So let us look at the graph, a portion of the graph, one period of the graph. So this should be, should look like this. So this is pi, this is 0, this is 2 pi. Okay, so take note that we have negative values located on this interval. Now, if you integrate from 0 to pi, you could show that, so this is the integral of sine. Here we are utilizing the Riemann integral. By the way, the Riemann integral and the Lebesgue integral coincides because this function is continuous. So the antiderivative, an antiderivative of the sine is a negative cosine. Evaluate from 0 to pi, so you get cosine of pi plus cosine 0, which is 2. Okay. However, if we integrate on the larger interval, this is not larger than the integral over 0 to pi because this is 0. Okay. So take note that here the area below, which you can think as the area, which is the same as the area of this above, it will cancel. Okay. So that's a counterexample where, or this is an example where you cannot relax or remove this condition here. So non-negativity is important for this property. Okay. Another property which is in the same spirit as with this property 6 is the what we call the Chebyshev inequality. So there are variants of the spelling of the name of Chebyshev, but we will choose this one. Okay, so if I take a positive epsilon and a simple function f in this pre-measure space with values in the Banach space y, then if I take the measure of the set where the norm is greater than the epsilon, then this is 1 over epsilon, less or equal to 1 over epsilon times the integral of the norm of f. Well, to see this, if we simply denote this by a, then applying the property a while ago, since f is greater than epsilon on this region, then the integral of the norm of f over a with respect to the measure mu is greater or equal to epsilon times the measure of b. So going back, this is precisely property 5, where alpha is taken to be epsilon and f is replaced by the norm of f. So this is basically property 5. Okay. Now, since the norm of f is a non-negative function if I integrate over the set x, which is larger than a, then the integral over x must be larger than the integral over a. So this is property 6. And that's indeed the proof. And you get it by dividing epsilon both sides. Okay. So that's the Chebyshev inequality. So looking at a geometrical interpretation, so suppose this is f, and I take, let's say, an epsilon, or we should say the norm of f, let us take an epsilon okay. By the way, this is not a simple function, so just think of it as the case of the general function first. So if we take, for instance here, the set of values that are greater or equal to epsilon, that would be this set here. And let us confine x on this region. So in this case, the inverse image where the norm is greater than epsilon would be this set here. Okay, so if you take the measure of this and multiply it by the height, then geometrically, that would be this region. So that would be the left-hand side. And take note that this is contained in the area over area under the curve over the set x. So indeed, the rectangular region is smaller than the upper or the blue region. Okay, so this is, as I said, not precise because here the norm of f is not a simple function, but later we will prove that the Chebyshev inequality is also valid for integrable functions that are not necessarily simple. Okay, and the last property would be the following. So if f is written in this representation, and this is sometimes called the canonical representation of f, so y times the indicator function, the inverse image of y, then since the indicator functions of the singletons are pairwise disjoint, one could show that the norm of f can be also represented in this way. Okay. And from this, you can now apply the triangle inequality with respect to the norm of y. So the norm of the integral of the simple function f is less or equal to the integral of the absolute or the norm of f over x with respect to the measure mu. So this can be deduced easily from the triangle inequality. So these are the properties of the Lebesgue-Bochner integral for simple functions. In the next lecture, we will discuss the completion of the simple functions.